Have you ever found yourself facing like a mountain of information articles, research, maybe even just your own notes, and wished there was a direct pipeline to the most important nuggets?
Yeah, absolutely. You want to quickly grasp the core ideas, right? Uncover the surprising facts, and really understand the big picture without getting bogged down in every single detail.
Exactly.
Mm.
If that sounds familiar to you, you are definitely in the right place today. We're doing precisely that. We're diving deep into one of the most exciting and transformative intersections happening right now. Artificial intelligence and machine learning meeting the world of material science.
That's right. And our focus today is specifically on how AI and ML are fundamentally changing the game for discovering, designing, and even manufacturing these cutting-edge materials.
We're talking about everything from the building blocks of new technologies like organic semiconductors to the really intricate processes that churn out the chips inside your phone, your computer, everything. And our mission for you, our listener, is basically to give you that shortcut. We're going to try and demystify the core concepts behind these powerful technologies, explore some truly surprising real-world applications, and hopefully reveal the incredible progress being made.
Think of it as your express lane, maybe, to being well-informed about a topic that's not just evolving, but actually reshaping our future.
So let's jump right in. Hashtag, tag, the grand challenge of materials design. Okay, so when we talk about developing new materials, especially something as advanced as, say, organic semiconductors or OSCs, it sounds way more complex than just mixing chemicals in a beaker, right?
Oh, definitely. It feels like trying to solve a puzzle with millions of pieces, maybe where each piece changes, depending on how you look at it.
Yeah, that's a good way to put it.
The real complexity lies in what researchers call the multi-scale and multi-dimensional complexities. It's about these relationships: synthesis, processing, structure, property, function.
Okay, break that down a bit. Synthesis processing.
Right. Imagine you're building a tiny, highly advanced machine. It's not just about picking the right parts, the right molecules. It's how those components are made, the synthesis. Then how they're put together, the processing. That dictates their resulting microscopic structure. And that structure gives rise to specific properties. And those properties determine how it ultimately functions in an application, like a solar cell or a display.
Wow. So changing one tiny thing early on.
Exactly. It can cascade through all those stages. It can completely alter the final material. Understanding just the molecular structure, for instance, doesn't automatically tell you how it will perform in a device. They're all interlinked.
So it's the ingredients, the recipe, the oven temperature, and how you shape the final cake, all interacting in these incredibly complex ways.
That's a great analogy.
Why focus so much research on these organic semiconductors, these OSCs? What makes them so important? Where do we actually see them?
Well, OSCs are incredibly versatile. Their big advantage is that you can finely tune their electronic, optical, thermal, and mechanical properties. It's like having a molecular toolkit. This makes them highly desirable across a huge range of applications that, touch our daily lives. Think about the screens you're probably looking at right now, your phone, tablet, TV. Many use OSCs in the displays or for efficient lighting like OLEDs.
Right, OLEDs.
They're also really crucial for future energy generation and storage. Think advanced flexible solar cells. You'll find them in highly sensitive sensors and, of course, in a vast array of next-generation electronics.
So they're kind of everywhere, or at least have the potential to be.
Their broad and growing impact really underscores why accelerating their development is so critically important.
Okay, so it's a deeply complex field, high stakes, applications shaping modern tech. But this brings us to a major roadblock you mentioned: data, or maybe the lack of good data, or sometimes the overload of unmanageable data.
You've absolutely hit on the core challenge. Traditionally, investigating these complex synthesis-to-function relationships has been incredibly difficult. Often, crucial metadata, that's the information about the experiment, the precise conditions, the nuances of a process, it gets overlooked.
Or just not written down properly.
Or underreported, exactly.
Right.
This makes it incredibly hard to reproduce experiments reliably or to build effectively on previous work. It's like trying to rebake that cake when you only have half the recipe and no oven temperature.
Right. And then paradoxically, you also have the opposite problem: too much data.
Precisely. On the other end, we have these rapid advances in characterization techniques, high-throughput experiments, computational modeling. They're generating just expansive increases of ever more intricate data.
Petabytes, you mentioned.
Yeah, massive amounts. And while that sounds like a good problem to have, it creates this enormous challenge of information overload. Traditional analysis methods simply can't keep pace with the sheer data deluge.
It's like trying to find a specific sentence in a library of a million books, but without a catalog or a search engine.
That's a perfect description.
So we're caught between not enough well-documented data and too much unanalyzed data. This clearly sets the stage for needing a different pathway for materials design and discovery, a new approach.
We need something to keep up with these immense challenges.
And that, of course, is where AI and machine learning step in, offering a completely new lens, really, to approach these problems. Okay, so let's bring in the hero of our story, machine learning. For anyone listening who might feel a bit, overwhelmed by the jargon, let's try to demystify it. What is machine learning really at its core?
At its most basic, machine learning algorithms learn from examples. Think of it like teaching a child through repetition and observation, rather than explicitly programming every single rule beforehand.
Okay, learning by seeing.
Exactly. These algorithms look for correlations, patterns, or try to develop knowledge directly from the training data they're given. And for chemical or material systems, these correlations, which can be simple straight lines or incredibly complex, nonlinear relationships, are found within a specific set of what we call physicochemical features.
Features. What kind of features are we talking about in material science? Can you give some concrete examples?
Sure. Features are essentially the measurable properties of a material or system that the algorithm uses to learn. They can range from something basic, like the chemical composition, what elements are in it, to its exact molecular structure, or the specific reaction or processing conditions used to create it, temperature, pressure, time, or even its inherent electronic or optical properties, like its band gap or how it absorbs light.
So the algorithm looks for links between these input features and the property we care about.
Precisely. It tries to find relationships between those input features and the material properties you're interested in predicting or maybe optimizing.
That makes sense. Finding hidden connections, maybe connections a human might miss just by looking. Now let's break down how this actually works in practice. Our sources mention an ML pipeline. Can you walk us through the essential steps?
Of course. The ML pipeline is a systematic process. Typically, it involves three main stages. First, very careful data preparation. Second, selecting the right ML method and actually building your model. And finally, evaluating how well that model performed.
And if it doesn't perform well?
Well, the beauty is it's often iterative. If the model's performance isn't satisfactory, you can go back, maybe refine your data, tweak the model, and repeat the steps to continuously improve its accuracy.
Okay, step one, data preparation. This sounds like the absolute foundation, the bedrock, right? Garbage in, garbage out.
Absolutely. Data preparation is critical. It directly impacts the accuracy and reliability of your ML model down the line. It's all about ensuring the data used for modeling is accurate, relevant, and suitable for the specific task you're trying to solve. And this involves several key stages itself.
So where do you even start with collecting data for these incredibly complex materials? It sounds like a challenge in itself.
It is. For robust ML models, you generally need large and reliable data sets. Databases are often the primary sources, and their careful design-defining terms precisely establishing relationships is crucial.
Right.
And to ensure broad access and usability, adhering to fair data standards is becoming really important. That means making data findable, accessible, interoperable, and reusable.
Fair data. Got it.
What's really fascinating now is how innovative methods, like using large language models, are enabling researchers to curate data directly from vast amounts of scientific literature, both structured and unstructured sources. This can accelerate the process immensely.
So mining papers automatically.
Essentially, yes. And specifically for organic semiconductors, the good news is there are several open access databases and datasets already available that provide a rich foundation for ML development.
Okay, so you've collected this huge amount of data, but I imagine it's rarely perfect right off the bat. That's where pre-processing comes in.
Exactly. Data pre-processing is vital because raw collected data often has issues, maybe redundancy, abnormal values, outliers, things that can really throw a model off track.
Right.
So this stage typically begins with data cleaning, identifying and removing irrelevant data points or outliers to create a more consistent, reliable data set. After cleaning, you usually apply data normalization or standardization.
What does that do?
It basically brings all the different features to a common scale. Imagine you have some measurements in nanometers and others in kilograms. They're on vastly different scales. Normalization adjusts them so the algorithm doesn't mistakenly think one feature is more important just because its numerical value is larger. It's essential for certain algorithms.
Okay, makes sense. Like converting everything to the same units before you calculate. And then there's this term, feature engineering. That sounds like taking the raw ingredients and getting them ready for the model to cook with.
That's a perfect analogy. Feature engineering is all about transforming that raw data into the actual features, those individual measurable properties that the model can use to learn effectively. The accuracy of any ML model really depends strongly on the quality and relevance of these features. They need to encode the system's structural and property characteristics in a way the algorithm understands.
How does that work? What are the steps in feature engineering?
It typically involves four main processes. First, creation, maybe calculating new features from existing ones, like a ratio or count. Second, transformation, like the normalization we just talked about, or maybe adjusting the distribution of a feature. Third, extraction. This is about distilling the most important information. And fourth, selection, choosing the most relevant features and discarding redundant or noisy ones.
Can you give an example of feature extraction? It sounds like finding the essence of the data.
Sure, think of feature creation as simple counting. Number of carbon atoms, number of rings in a molecule, maybe its molecular weight. Transformation, as we said, might be scaling or adjusting skewness. For extraction, imagine you have dozens of measurements describing a molecule's shape. Maybe many are correlated. Principal component analysis, or PCA, is a common technique here. It takes those dozens of features and finds, say, the 2 or 3 underlying combinations or principal components that capture most of the variation. It reduces complexity without losing too much information.
So simplifying the picture for the model.
Exactly. And finally, feature selection is about removing features that don't add much value or are just duplicates, making the model more efficient. What's exciting now, especially with deep learning, is that automated feature engineering is becoming more common. It takes some of the manual effort out and improves reproducibility.
Streamlining that crucial step. Okay, so data collected, cleaned, features engineered. Now, I understand you don't just feed all this precious data into the model at once. There's this concept of data splitting.
Precisely. After all that preparation, the processed dataset is partitioned, usually into 3 distinct non-overlapping groups: training data, validation data, and test data.
Okay, 3 groups. What are the typical ratios?
Common splits might be something like 60% for training, 20% for validation, and 20% for testing, or maybe 80.7 It depends on the total amount of data you have and the specific goals.
Why split it? Why not just train on everything to make the model as smart as possible?
Good question. The training data is indeed the largest portion, and that's what the model actually learns from. It's where the algorithm identifies the underlying patterns and relationships by iteratively adjusting its internal parameters.
Okay.
The validation data is used during the training process, but indirectly. It's used to tune the model's hyperparameters. These are like the settings or knobs on the model, things like the learning rate or how complex the model structure should be, like the number of layers in a neural network.
Why tune them separately?
Because validation data is crucial for preventing a major pitfall called overfitting. That's where the model learns the training data too well, including its noise and specific quirks, so it performs brilliantly on data it's already seen but fails miserably on new, unseen data. Validation helps find the sweet spot, preventing overfitting and also underfitting, where the model is too simple.
So validation is like practice quizzes to make sure it's learning generally, not just memorizing. What about the test data then?
The test data is the final exam. It's a completely independent set of data that the model has never seen during training or validation. It provides the final, unbiased evaluation of how well the model is likely to perform in the real world on brand new data. It tells you how well the model has truly generalized.
That makes perfect sense. A really thorough process just to prepare the data. Now, let's get to the actual learning part, ML method selection and model construction. How do we teach the model?
Right. So during training, the ML model learns those relationships between the input features and the target outputs we care about. It does this by adjusting its internal parameters to minimize prediction errors, aiming ultimately to generalize well to new, unseen data.
And how do we choose which ML method to use? There seem to be many different types.
The methods are broadly categorized based on whether you have labeled data. Labeled data means you already know the correct answer or output for each data point in your training set.
Like having flashcards with the answer on the back for the model to learn from.
Exactly like that. That's called supervised learning, or SL. In SL, the data points come with their corresponding labels or target variables, and the model is trained to predict those labels accurately.
Okay. And supervised learning does different things.
Right. SL can be further divided into 2 main task types. First is classification, where the goal is to predict discrete categories or classes. The second is regression, where the goal is to predict continuous numerical outputs.
Can you give us some quick, concrete examples of classification and regression in material science?
Sure. For classification, you might train a model to predict if a newly designed organic molecule is likely to be synthesizable under certain conditions, a yes-no prediction. Or maybe classify a material as either a metal or a semiconductor based on its features.
Okay, distinct categories.
For regression, you're predicting a number on a continuous scale. For instance, predicting specific molecular properties like their exact orbital energies, their band gaps, or even things like their heat capacities.
Got it. And what about the specific algorithms that do this? I hear terms like SVMs, random forests, neural networks thrown around.
Those are definitely some of the workhorses. Support vector machines, or SVMs, are often used for classification. They work by finding the best possible dividing line or hyperplane in a high-dimensional space to separate different categories of data points, aiming for the widest possible margin between them.
Like drawing the sharpest boundary.
Exactly. Then you have random forests, or RFs. These are what we call ensemble methods. They're like a committee of experts. Instead of relying on a single, potentially complex decision tree, an RF builds many individual decision trees on random subsets of the data and features.
Okay.
Each tree makes a prediction, and the final output is typically the average for regression or the most common vote for classification across all the trees. This ensemble approach makes them very robust and much less prone to overfitting than single decision trees.
A wisdom of the crowd approach, kind of.
In a way, yes. And finally, artificial neural networks, or ANNs, are inspired by the structure of the human brain. They consist of layers of interconnected nodes, or neurons. They are incredibly powerful at capturing complex, nonlinear relationships hidden within data.
And they come in different flavors.
Yes, there are various architectures. Feed-forward neural networks, FNNs, are common. Convolutional neural networks, CNNs, are excellent for grid-like data, like images or spectra. Graph neural networks, GNNs, are specifically designed for data represented as graphs, like molecules. Deep neural networks, DNNs, just refer to networks with many layers. Recurrent neural networks, RNNs, are good for sequential data.
Wow, lots of options. Do ANNs have downsides?
They generally require significant amounts of training data to perform well, and they can be computationally intensive to train. But their power in modeling complex systems is immense.
Okay, that covers supervised learning with labeled data. What if you don't have the answers readily available? What if the data is unlabeled?
That's where unsupervised learning, or USL, comes in. USL algorithms work with unlabeled data. The model has to find meaningful patterns, structures, or relationships within the data entirely on its own, without any explicit guidance or correct answers provided.
So you just give it the data and say, find something interesting.
Pretty much. Common USL tasks include clustering. This involves grouping similar data points together based on their features. For example, you could use clustering to automatically classify different crystal packing arrangements, polymorphs, of the same molecule, or maybe group scientific papers based on their text content using natural language processing to find hidden thematic similarities. K-means is a popular clustering algorithm.
Finding natural groups in the data. What else?
Another key USL task is dimensionality reduction. As we touched on with feature extraction, this aims to reduce the number of input features while preserving as much essential information as possible. Techniques like PCA we mentioned earlier can be used here, but also others like lasso or CISO.
Why reduce dimensions?
It improves computational efficiency, helps prevent overfitting by removing noise, and crucially, it can make complex, high-dimensional data much easier to visualize and understand. You can sometimes plot the reduced dimensions and see patterns emerge.
That sounds really useful. Is there anything in between supervised and unsupervised?
Yes, there's semi-supervised learning, or SSL. This approach trains models on a mixture of a small amount of labeled data and a large amount of unlabeled data. It's particularly useful in situations where getting labels is expensive or time-consuming, but unlabeled data is plentiful.
A practical compromise.
And then there's a different paradigm altogether. Reinforcement learning, or RL. Here, the model, often called an agent, learns to make a sequence of decisions by interacting with an environment. It receives rewards for good actions and penalties for bad ones, learning over time to maximize its cumulative reward. Think about training a robot to navigate a maze or teaching an algorithm to play chess.
Learning by trial and error, essentially.
Yeah.
Okay, that's a great overview of the methods. So once the model is trained using one of these approaches, how do we actually know if it works? How do we evaluate its performance?
Right, evaluation is absolutely critical. You need to rigorously assess the algorithm's performance on the specific task it was trained for, and do it in an unbiased way, usually using that held-out test set we talked about.
How is that assessment done?
There are several evaluation methods. The simplest is the simple holdout method, where you just use the single test set. But more robust methods involve cross-validation, like k-fold cross-validation.
K-fold.
Yeah. You split the entire data set, excluding the final test set, into k equal-sized chunks or folds. Then you train the model k times. Each time, you use one fold as a temporary validation set and the remaining k1 folds for training. You rotate which fold is the validation set each time.
Okay, so you test it on different parts of the day.
Exactly. This gives you a more robust estimate of the model's performance because you've tested its generalization ability across different subsets of the data. There's also leave one out cross-validation, which is an extreme case where k equals the number of data points.
And how do we quantify that performance? What are the key numbers or metrics that tell us how good the model actually is?
It depends on the task. For classification tasks, performance is often measured by accuracy, simply the percentage of predictions it got right. Or the flip side, the error rate. You might also look at a confusion matrix, which breaks down the types of errors like false positives and false negatives, which is often more informative than just accuracy alone.
Okay, for sorting things into boxes, what about predicting numbers for regression?
For regression models, where you're predicting continuous values, key metrics measure how close the predictions are to the actual values. Common ones include root mean squared error, RMSE, and mean absolute error, MAE. Both tell you the typical magnitude of the prediction error, but RMSE penalizes larger errors more heavily.
Lower error is better, obviously.
Right. We also often look at the correlation coefficient, usually denoted as R squared, R2. This indicates the proportion of the variance in the actual values that is predictable from the model's predictions. And R2 of 1 means perfect correlation, while 0 means no correlation.
So these metrics give us a concrete way to understand not just if the model works, but how well it works, and maybe where its weaknesses are.
Precisely. They are essential for comparing different models and for building confidence in their predictions.
Okay, with that solid primer on the ML toolkit, let's dive into some specific, really fascinating applications. Let's start with organic semiconductors, OSCs. This is where the rubber meets the road, right? How is ML specifically helping design new molecules with targeted properties, moving beyond just trial and error in the lab?
Absolutely. This is where AI truly shines and accelerates discovery. ML models are now routinely used to predict crucial properties of OSCs and even their building blocks, things like their electronic behavior, how easily they gain or lose electrons, redox properties, how they interact with light, optical properties, and even their mechanical characteristics.
So you can basically design a molecule on a computer and get a good idea of how you'll behave before making it.
That's the goal, and we're getting remarkably good at it. Imagine knowing its precise properties, how well it conducts electricity, what color light it emits before you even step into a lab to synthesize it. This saves immense amounts of time, resources, and effort.
That's incredible. What kind of inputs do these models need to make such precise predictions? How does an algorithm see a molecule?
It typically uses numerical representations derived from what we call molecular descriptors. These can be relatively simple, like counting the number of atoms of a certain type or the number of aromatic rings in the molecule. Or they can be quite complex, like detailed maps of charge distribution across the molecule derived from quantum chemistry calculations. Another popular approach is using molecular fingerprints.
Fingerprints, like for humans.
Sort of. They're numerical signatures that encode structural information about the molecule in a unique vector. Extended circular fingerprints, or ECFPs, are a common type. They capture information about the local atomic environments within the molecule.
Okay.
And sometimes, models can even work directly with SMILE strings. That's the Simplified Molecular Input Line Entry System, essentially a text-based way of representing a molecule's structure. Using SMILEs directly can reduce the need for complex manual feature engineering.
So different ways to translate a molecule into numbers the AI can understand. Can you give us some concrete examples of these predictions in action? How accurate are they?
Certainly. For instance, deep neural networks, DNNs, have been trained to predict a property called intramolecular reorganization energy, or RE. This is a really vital property for understanding how easily charged carriers, electrons, or holes can move within a single OSC molecule, which impacts conductivity. These DNN models have achieved very high accuracy, with predictions showing excellent correlation, an R2 value of 0.92, and low error, around 12 millielectron volts, compared to theoretical calculation.
That sounds incredibly precise.
It is. Similarly, simpler feed-forward neural networks, FNNs, have been used to analyze and predict something called dynamical disorder, which is another key factor affecting how charges move through the material over time. And more advanced models, like message-passing neural networks, or MPNNs, these are a type of graph neural network, are being used to predict the subtle electronic interactions between molecules in an OSC crystal.
Interactions between molecules, okay.
Right. And knowing these intermolecular electronic couplings helps us predict things like charge carrier anisotropies, meaning whether charge moves more easily in one direction within the crystal than another. This level of predictive power significantly accelerates the whole research cycle.
I could see that. And I imagine with the sheer number of possible molecules out there, the chemical space is just astronomically vast. These models must be fantastic for just narrowing down the search, like a pre-screening tool.
Exactly. That's one of their most powerful applications. ML models act as powerful pre-screening tools, drastically reducing the chemical space that needs to be explored with more resource-intensive methods, whether it's detailed quantum chemistry calculations or actual lab experiments.
Right.
There's an impressive example where a neural network pre-screened a staggering 1.6 million molecular candidates. The goal was to find molecules suitable for thermally activated delayed fluorescence, or TADF, which is important for efficient OLEDs.
1.6 million. That sounds like a classic needle in a haystack problem. How did the AI do?
It did remarkably well. The neural network predicted a key property related to TADF performance, and its predictions showed excellent correlation, R2 equals 0.94, with the results from much slower, more expensive, time-dependent density functional theory calculations. This allowed the researchers to focus those intensive calculations only on the most promising candidates identified by the AI.
So the AI acted like a really effective filter.
Precisely. Several top candidates were then selected for synthesis and experimental testing. But what's really notable here, and something the original researchers strongly emphasized, is that this success wasn't just about the algorithm.
What else was involved?
It was a true convergence of diverse domain expertise. You had synthetic chemists, device scientists, quantum chemistry experts, ML specialists, all collaborating, even with industrial partners. It really highlights the crucial role of this human-machine collaboration. It's not just machines replacing scientists, but machines working with human experts to achieve breakthroughs faster.
That's a fantastic point. As a partnership, leveraging the strengths of both. Beyond just predicting properties of existing or slightly modified molecules, can AI actually create brand new molecules, designing them from scratch for specific jobs?
Yes, absolutely. That's where the power of generative models comes into play. Models like variational autoencoders, or VAEs, and generative adversarial networks, or GANs, are being used for designing entirely novel molecular structures that haven't existed before.
How do VAEs work in this context?
VAEs learn a compressed representation, or latent space, of molecular structures, often starting from SMILE strings. They have two parts: an encoder that compresses the molecule into this latent space, and a decoder that reconstructs a molecule from the latent space representation. By optimizing points within this latent space for desired properties, the decoder can then generate new molecular structures predicted to have those target properties, like specific electronic characteristics or light emission wavelengths.
So it learns the essence of molecules and then generates new ones with desired features.
Ah.
What about GANs? They have that generator-discriminator setup, right? How does that help create molecules?
GANs operate through this fascinating adversarial dynamic. You have a generator network that tries to create new, realistic molecular designs. And you have a discriminator network that acts like a critic. Its job is to distinguish between real, known molecules from a database and the fake ones created by the generator.
A constant competition.
Exactly. The generator tries to fool the discriminator, and the discriminator tries to get better at spotting fakes. This constant feedback loop forces the generator to learn how to produce increasingly realistic and novel molecules that satisfy specific criteria you set, like having certain electronic properties or fitting within defined structural constraints.
So you can guide the generation process.
Yes. For instance, GANs have been successfully used to design new fluorescent organic molecules or to generate vast libraries of potential donor-acceptor oligomers with specific target dipole moments and desired energy gaps. They really open up exploration of entirely new chemical spaces.
That sounds like an AI chemist sketching out new possibilities. What about reinforcement learning? How does that fit into discovering new molecules?
Reinforcement learning frameworks, like one called Reinvent, are proving incredibly powerful, especially when combined with high-throughput calculations. The RL agent learns to generate molecules step by step, receiving rewards based on whether the generated molecule has desirable properties predicted by computational models.
Learning by doing, rewarded for good designs.
Precisely. A fantastic example is the discovery of new anthracene derivatives designed specifically for singlet fission, SF, or triplet annihilation, TTA. These are processes crucial for advanced solar cells and displays, requiring very specific excited state energy levels. The RL models were able to generate dozens of completely novel compounds predicted to have these desired characteristics, pushing the envelope for materials with tailored energy conversion pathways.
That's amazing. It's not just about the single molecule, though, is it? How molecules arrange themselves in solids and crystals is hugely important. Crystal structure prediction sounds incredibly complex, like predicting how millions of tiny magnets will arrange themselves perfectly.
It is indeed a significant challenge, often called the CSP challenge, but ML is making inroads here too. Kernel-based ML techniques, often combined with clustering and dimensionality reduction methods, are being used to map out vast crystal packing landscapes. Yeah, essentially mapping the different ways a molecule could potentially pack together in a crystal and the energy associated with each arrangement. This allows us to potentially predict multiple possible crystal structures, or polymorphs, as they're called, for a given molecule.
So finding different stable or metastable arrangements.
Exactly. And we can even start to predict the properties associated with each polymorph, potentially even before they're synthesized in the lab. Creating these energy structure function maps is a game changer for understanding how molecules will behave in the solid state and how that impacts their function in a device.
That's incredible foresight. And speaking of the solid state, our sources really highlight the critical role of thermal properties for crystallization. Why are thermal properties like melting point so important here?
This is absolutely crucial for device performance, especially in organic, thin films used in electronics. Highly crystalline films generally have much better charge carrier mobility, how easily charges move, and longer excitant diffusion lengths compared to disordered amorphous films. Better order means better performance.
Okay, crystalline is good. But are all crystals created equal? The sources mention desirable platelet versus undesirable sphere-like crystals.
That's a key distinction. Within crystalline films, the specific morphology, the shape and structure of the crystals matters immensely. What you ideally want are platelet crystals. These are large, often single crystal domains, maybe tens to hundreds of microns across. They exhibit uniform, long-range order and have very few internal defects or grain boundaries where charges can get trapped or recombine.
So smooth highways for charges.
Exactly. This leads to high-performance devices. In stark contrast, you have spherulite crystals. These generally have much worse charge carrier mobility. They're often riddled with voids and pinholes, which can lead to electrical shorts and really compromise device yield and reliability. They might look like rough, disorganized aggregates or sometimes sharp, needle-like formations.
Definitely want to avoid those. So platelets are the gold standard for high performance, reliability, efficiency. But how does AI help us actually get them? It sounds like a very specific, difficult target to hit experimentally.
It is. The key insight that researchers uncovered, linking back to thermal properties, is that two specific properties correlate strongly with this desired platelet morphology. The crystallization driving force, often denoted IgC, and the melting point, TEM.
Okay, driving force and melting point, how do they correlate?
Generally, materials with a high crystallization driving force, meaning a strong tendency to crystallize, and a high melting point, tend to crystallize as those coveted platelets.
Right. But how easy is it to know those values?
Well, melting point in FAMTM is often readily available or relatively easy to measure. But the crystallization driving force is much harder to determine experimentally for a large number of compounds. And this is precisely where ML provides a significant advantage, allowing for rapid, virtual screening based on predicted thermal properties.
So ML can predict these crucial thermal properties.
Yes. And there's a fantastic real-world success story that brilliantly illustrates this. It really shows AI accelerating discovery in a very tangible way.
Tell me about it. This sounds like a breakthrough.
Researchers trained machine learning models specifically, a type called gradient boosting decision trees, using the XGBoost algorithm on massive datasets. They had melting points for over 267,000 molecules and enthalpies of melting, related to DHE, for about 5,000 molecules.
Wow, that's a huge amount of data for the models to learn from. What does they do once the models were trained?
The models achieved impressive accuracy in predicting these thermal properties just from the molecular structure. So the researchers then used these trained models to virtually screen a colossal library, 462,000 commercially available organic molecules.
Screening almost 500,000 molecules, how do they narrow it down?
They applied a smart heuristic rule based on the insight about platelets. They looked for molecules predicted to have a high melting point, TMO 550 Kelvin, and a strong crystallization driving force, 7.5 kilojmol. This drastically narrowed that enormous pool down to just 44 candidates predicted to be good platelet formers.
From 462,000 down to 44, that's some serious filtering. How did it pan out in the real world, in the lab? Were the AI's predictions accurate?
They chose 6 of these 44 candidates for experimental validation, actually making them and seeing how they crystallized. The results were remarkably encouraging. 3 of the 6 crystallized exactly as desired, forming large area platelets. 1 formed a spherulite, and 2 resisted crystallization altogether under the tested conditions.
So 3 out of 6 worked as predicted for platelets.
Yeah.
That's a 50% success rate.
Exactly. A 50% success rate in identifying ideal platelet-forming organic materials from commercially available options. Considering how difficult and complex this challenge is, that's an excellent result. It's a massive leap forward compared to traditional trial and error, which could take years.
That's genuinely impressive, a huge acceleration. But was it perfect? Did the AI hit every single target flawlessly, or were there surprises?
Not entirely flawless, and this is where it gets interesting, highlighting the ongoing complexities and the vital need for human insight. There was one specific molecule, abbreviated TBT. The ML model predicted it should form platelets based on its structure. However, when its thermal properties were measured experimentally, the values actually placed it in a region on their map where one would typically expect it to resist crystallization. It didn't meet the empirical criteria they'd established.
Oh, so the prediction was wrong.
Well, here's the twist. Despite its measured properties falling in the resist crystallization zone, TBT still formed those desirable platelets in the experiment.
Wow. How does that happen?
It highlights factors that current ML models, or at least the ones used in that study, don't yet fully account for. Things like polymorphism, the ability of a material to exist in multiple different crystal forms, some stable, some metastable. Perhaps TBT forms a metastavable platelet structure under those specific conditions. These nuances are still challenging to predict purely computationally.
So the AI gets you most of the way there, but expert knowledge and experimental validation are still indispensable.
Absolutely. The key takeaway from this success story, strongly emphasized by the researchers themselves, is the power of merging machine and human intelligence in collaborative discovery. The ML significantly narrows the search space, suggests promising avenues you might never have considered, but human expertise is still critical for interpreting results, troubleshooting unexpected outcomes like TBT, and making the final selections. It's a partnership.
Okay, we've talked about designing the materials themselves. Now let's shift gears to the factories where they're made. Semiconductor manufacturing. This is an industry famously driven by Moore's Law, the idea that the number of transistors you can pack onto a microchip doubles roughly every 2 years. But keeping that pace up is getting harder and harder, isn't it? It feels like we're bumping up against fundamental limits.
It absolutely is getting tougher as semiconductor devices become incredibly smaller and more intricate, evolving from the relatively simpler planar 2D MOSFETs to complex 3D structures like FinFETs, and now to cutting-edge gate-all-around FETs. The manufacturing process flow becomes, as the sources say, much more complicated.
More steps, tighter tolerances.
Exactly. This relentless scaling necessitates much tighter specifications at every single step. It introduces entirely new potential failure modes, and it generates just massive amounts of data throughout the production line. From the initial silicon wafer production to the final device assembly and testing, data is pouring out of sensors and metrology tools.
And historically, what happened to all that data?
Historically, much of this data remained largely unanalyzed. It was collected, maybe archived, but not fully utilized to optimize processes in real time. It represents this huge, untapped resource just sitting there on the factory floor.
So if there's this massive, largely unanalyzed data trove, what's ML's role here? Is it about finding the useful signal in all that noise?
Precisely. Machine learning provides the tools to extract actionable information and crucial insights from this data deluge. By doing so, it can significantly reduce costs associated with defects, rework, scrapped wafers. It can dramatically improve overall wafer yield and quality, which is the foundation for all chips, and it can significantly enhance cycle time.
Cycle time, meaning how fast chips get through the factory.
Exactly. How quickly you can move from raw silicon to finished product. ML is about making the entire incredibly complex process more efficient, more predictable, and ultimately more resilient to problems.
Let's get specific then. How does ML actually optimize these manufacturing processes step by step, from the raw wafer to the final device?
Okay, in terms of process optimization, ML is proving invaluable right from the start with improving wafer yield and quality. For example, studies have used ML models techniques like adaptive boosting, gradient boosting, random forests, decision trees to intelligently optimize the time management and scheduling of various manufacturing machines, achieving accuracy improvements up to 97.8% in predicting optimal schedules.
Making the factory flow better.
Yes. ML also significantly aids in what's called advanced process control, or APC. For instance, in intricate etching processes where you're carving tiny patterns, ML-based APC can lead to measurable improvements in critical dimension uniformity, or CDU basically ensuring those patterns are exactly the right size everywhere across the wafer. One study showed a 3.9% improvement for specific patterns.
That sounds small, but I imagine at these scales, 3.9% is huge.
It can be the difference between a working chip and a failed one, absolutely. Another interesting application is in atomic layer deposition, or ALD, a technique for depositing ultra-thin films one atomic layer at a time. Here, Bayesian regularized artificial neural networks, or BRANs, are being used for process development.
Why brands specifically?
They offer a good balance. They can capture the complex relationships in ALD without requiring the massive computational power often needed for highly detailed physics-based simulations, while still providing very satisfactory predictive results for process optimization. It speeds up development significantly.
So, optimizing the process as it happens. What about preventing problems before they happen, like predicting when a machine might break down, or even using ML to enable totally new kinds of devices?
ML is proving excellent for malfunction detection and prediction. By analyzing sensor data from manufacturing tools, ML models can predict potential failures before they occur. Studies using decision trees, support vector aggressors, SVRs, and Bayesian networks have shown they can cut equipment downtime by a significant 12–21%.
That translates directly to cost savings and keeping production running.
Huge savings, yes. Imagine avoiding a costly, unscheduled production halt because the system alerted maintenance engineers to a potential breakdown days in advance. And looking even further ahead, there's this really exciting example of electronic skin, or e-skin.
E-skin, what's that?
It's a flexible material embedded with sensors. One project utilized a 6-layer artificial neural network to create an advanced intelligent material cognition system. This e-skin could identify multiple different gases and volatile organic compounds simultaneously, with a capability that, in some aspects, the researchers claimed surpasses that of humans.
Wow.
It truly showcases the potential for ML, not just in manufacturing, but in creating advanced, intelligent materials themselves that can sense and react to their environment in really sophisticated ways.
That e-skin sounds almost like science fiction becoming reality.
Yeah.
Switching back to quality control within the factory, what exactly are virtual metrology and predictive metrology? They sound like ways to check quality without physically measuring every single thing.
That's essentially right. They are powerful techniques for ensuring quality and speeding up the feedback loop in production. Virtual metrology, or VM, is about estimating product or process properties using indirect measurements and advanced modeling. Instead of taking a wafer out of the production line for a costly, time-consuming, and sometimes even potentially damaging physical measurement, VM uses readily available sensor data from the process tool itself to predict the property you care about.
Like predicting film thickness while it's being deposited.
Exactly. VM can predict film thickness during deposition using models like SVR or neural networks. It can also be used to identify wafer surface defects using automatic defect classification, or ADC systems. These often use convolutional neural networks, CNNs, to analyze images from inspection tools, classifying defects nearly without human intervention. The key benefit of VM is providing real-time or near real-time feedback, enabling faster decisions and immediate process control adjustment.
Faster feedback loops. Okay, and how is predictive metrology, PM, different from VM?
Predictive metrology, or PM, takes this a step further, aiming to predict quality metrics much earlier in the process, sometimes months before traditional final electrical tests would reveal a problem. For example, PM might shed light on probing critical electrical properties, like the tiny capacitance of a trench structure on a chip, based on measurements taken during the fabrication steps, long before the device is fully assembled and tested.
predicting future problems based on early indicators.
Precisely. Another example is in lithography, a critical patterning step. A tree-based model called LightGBM was used for outlier detection, finding wafers that deviated significantly from the norm. This PM approach allowed the factory to reduce the sampling rate for physical inspections by up to 70%, saving time and money, while still achieving 100% outlier detection, albeit with a manageable 15% false alarm rate. These techniques are vital for proactive quality control.
Catching problems early, reducing waste, improving efficiency. It sounds like neural networks are popping up quite a bit in these manufacturing applications. Is there a clear trend towards using them?
Absolutely. The systematic reviews referenced in our sources make it quite clear. Neural networks are emerging as the most popular models approaches for semiconductor manufacturing optimization.
Why is that? What makes them so popular in this field?
It boils down to two main things: their capability to accomplish a greater number of tasks compared to some simpler models, and their inherent strength in handling complex, nonlinear data with significantly higher accuracy. Semiconductor manufacturing data is often highly complex and nonlinear, and NNs excel at finding patterns in that kind of data.
And what kind of data are they typically learning from?
Interestingly, they are predominantly used to learn from optical spectra data. This could be data from ellipsometry, scatterometry, or optical emission spectroscopy, OES, generated during processes like etching or deposition. These optical signals contain a wealth of information about the process state and the wafer properties, and NNs seem particularly adept at extracting those insights, regardless of the specific process step or the end goal, like control or prediction.
So neural networks are often the best choice then. Are they kind of the silver bullet for semiconductor manufacturing AI?
They certainly show superior performance in many direct comparisons mentioned in the literature. For example, CNNs were shown to significantly outperform traditional methods like ridge regression when used for advanced process control, or virtual metrology based on OES data achieving an R-squared of 0.91 compared to zero point 0.8 for ridge regression.
That's a noticeable difference.
Definitely. Similarly, NNs often outperform support vector regressors and simple linear regression for tasks like controlling the chemical mechanical polishing (CMP) process, achieving higher R-squared values for predicting critical parameters like dishing and erosion.
Okay.
However, it's important not to overstate it. While NNs are incredibly powerful and often lead the pack, other ML methods like random forests can also yield top-tier results in certain contexts. Random forest, for example, is frequently highlighted as being very effective for overall factory yield prediction.
So it's not always NNs.
No. The best tool still depends heavily on the specific problem you're trying to solve, the nature and amount of data you have available, and practical considerations like computational resources and interpretability requirements. But the trend towards NNs, especially for complex spectral data analysis, is undeniable.
Okay, so we have this growing toolbox of powerful AI methods, NNs, random forests, SVMs, and others. But when a researcher or engineer is faced with a new materials optimization problem, how do they know which tool to pick? Especially when running real lab experiments is so costly and time-consuming. How do they benchmark success efficiently?
That's a critical question, and it leads us to approaches designed specifically for guiding experiments intelligently. One key method here is Bayesian optimization, or BO. Think of it as an active learning strategy that acts like a highly intelligent experimenter.
An intelligent experimenter, how so?
Instead of just randomly trying different combinations of parameters or blindly following a predefined grid search, BO intelligently selects the next experiment to run based on what it has learned so far. Its goal is to find the optimal conditions, the best material or process parameters in the fewest possible experimental iterations.
How does it decide which experiment to run next? What's the smart part?
BO works with two core components. First, it builds a surrogate model, usually a probabilistic model like a Gaussian process, to approximate the unknown relationship between the input parameters and the output property you want to optimize. This model essentially creates a rough map of the experimental landscape based on the limited data points you've already collected, and it also estimates the uncertainty in its predictions.
Okay, a map with uncertainty.
Right. Second, it uses an acquisition function. This function leverages the surrogate model's predictions and its uncertainty estimates to decide which experiment is most likely to yield the biggest improvement or provide the most information to reduce uncertainty in promising regions. It balances exploring unknown areas with exploiting areas already known to be good.
So it's making strategic choices based on the current map.
Exactly. This makes BO incredibly data efficient. It tries to maximize the knowledge gained from each precious experiment, which is crucial in material science where experiments can be expensive, slow, or very difficult to perform.
That sounds like a much smarter way to explore than just trying things randomly. Now, a recent comprehensive benchmarking study really dug into this, comparing different Bayesian optimization approaches head-to-head. What did they find in this battle of the models, particularly comparing Gaussian process with something called automatic relevance detection, or GPARD, versus random forest used within BO?
Yes, this was a really valuable study. They tested these algorithms across 5 diverse, real-world experimental materials datasets covering things like carbon nanotube polymer blends, optimization of 3D printed structures, and others. It wasn't just theoretical.
And what was the main takeaway?
The key observation was that Gaussian process with automatic relevance detection, GPARD, which uses what are called anisotropic kernels, and random forest, RF, when used as the surrogate model within the BO loop, showed comparable overall performance in finding the optimal materials or conditions.
Comparable, so neither was definitively better across the board.
In terms of final outcome, they were often neck and neck. And importantly, both of these methods significantly outperformed the commonly used standard Gaussian process model that uses simple isotropic kernels. So using either GPARD or RF was much better than the basic GP approach.
How did they actually quantify that performance? How did they measure better or faster in finding the best materials?
They used several metrics. One useful one was top percent, which tracks the fraction of the known top-performing candidates in the dataset that the algorithm manages to discover within a certain number of experiments, the budget. This metric reveals how quickly an algorithm learns and homes in on the best solutions.
What did the top percent results show?
They showed that GPARD and Random Forest achieved an impressive 80% discovery rate of the top candidates using significantly fewer experiments, roughly 75 to 85 samples on average across the datasets. In contrast, the standard GP model, without ARD, using isotropic kernels, needed about 170 samples to reach that same 80% discovery rate.
Wow, so roughly twice as efficient.
Exactly. They also calculated metrics like enhancement factor, EF, and acceleration factor, AF, to quantify the performance gain compared to just doing a random search. GPARD and RF showed acceleration factors up to 8 times faster than random searching, highlighting their efficiency.
That's a huge improvement in efficiency. But here's something interesting. You said they had comparable overall performance. Does that mean they arrived at the best solutions by following the same path through the experimental space?
This is where it gets really fascinating. The study found that even when GPARD and Random Forest achieved similar final results, they often took very different paths to get there. They explored the materials design space in distinct ways.
How do they measure that?
They used something called the Jacquard Similarity Index, which measures the overlap between the sets of experiments chosen by each algorithm at different budget points. The low Jacquard indices indicated that the sequences of experiments selected by GPARD and RF were often quite dissimilar.
What does that imply practically?
It highlights a crucial point. The optimal BO algorithm selection varies with the assigned experiment budget and the specific optimization task. An algorithm that might be best for quickly finding some good solutions early on, exploration, might not be the most efficient for precisely fine-tuning the absolute best solution later, exploitation, and vice versa. The best choice depends on your goal and resources.
That's a really powerful insight. Choosing the right tool isn't just about the final destination, but also about the journey, the strategy the model uses. So what explains these divergent paths to success? Why do GPARD and RF behave differently even when they end up in a similar place? Let's dig into the why behind the model choice.
There are several fundamental differences between Gaussian processes and random forests that explain their different behaviors within BO. First, let's consider their underlying distributional assumptions.
Assumptions about the data.
Yes. Gaussian processes inherently rely on assumptions of Gaussian normal distributions when they make predictions of the mean output and, crucially, the standard deviation or uncertainty around that prediction. Random forests, on the other hand, are essentially distribution-free. They don't make strong assumptions about the underlying data distribution. They work by aggregating predictions from an ensemble of many decision trees.
How does that difference matter in practice?
It means RFs can sometimes more accurately capture complex relationships that aren't smooth or normally distributed situations with sharp jumps, piecewise constant behavior, or features that span orders of magnitude. These are actually quite common in real-world materials data. GPs, with their inherent smoothness assumptions tied to the kernel function, might tend to smooth over these sharp changes.
Okay, so RF might be better for messy, jumpy data. What about computational demands? How do they scale if you have lots and lots of experiments?
That's a very significant practical difference, especially for high-throughput experiments generating data rapidly. Random forest is generally much quicker to train. Its computational complexity scales roughly as O(n) log n, where n is the number of data points experiments run so far.
Okay, fairly efficient. What about Gaussian processes?
Standard Gaussian process models have a cubic complexity, scaling as O(n)(3). This means that as your number of experiments grows, the time needed to train the GP model increases much, much faster. For very large data sets, say 105 or 106 data points, which might occur in large virtual screenings or long autonomous experiments, GP's cubic complexity can become intractable, just too slow to be practical, especially if you need to retrain the model quickly to decide the next experiment in real time.
So RF has a definite advantage for large data sets or real-time optimization where speed matters.
Yes, the faster training time of RF can be a significant advantage in those scenarios.
What about setting these models up initially? Is one easier to tune or get working well than the other? Maybe for someone who isn't a deep ML expert?
That's another practical consideration highlighted by the study. Random forest generally requires less effort in initial hyperparameter selection. It's often less sensitive to the exact choice of settings, like the number of trees or the depth of each tree, and you can often get pretty good results with default or easily tuned parameters. It's considered less penalized for suboptimal choice.
Easier to get started with, perhaps. What about GP?
In contrast, Gaussian process models require careful selection of the kernel function. The kernel essentially defines the model's assumption about the smoothness and correlation structure of the underlying function you're trying to model. Choosing an inappropriate kernel can introduce unverified smoothness assumptions about the unknown materials design space, which might actually slow down the optimization process or lead to suboptimal results. RF avoids making such strong prior assumptions.
So RF might be a bit more robust if you don't know much about the underlying landscape you're exploring. Now, you mentioned earlier that GP with anisotropic kernels, GPARD, performed much better than GP with isotropic kernels. What's the big deal with these anisotropic kernels? You call them an unsung hero.
They truly are. The benefits of using GP with anisotropic kernels, the ARD part, are substantial and quite insightful. Anisotropic just means direction dependent.
Okay.
Standard isotropic kernels assume the function changes similarly in all input dimensions. They use a single length scale parameter to describe correlation. ARD, however, allows for individual characteristic length scales for each input feature dimension.
So separate length scale for temperature, pressure, concentration, etc.
Exactly. And these individual length scales act like learned weights or measures of relevance for each feature. A very small length scale for a particular feature implies that the output function changes rapidly with small changes in that feature, meaning it's a highly sensitive or relevant feature. A large length scale suggests the function is less sensitive to changes in that feature.
So the model learns which features are most important.
Precisely. ARD stands for Automatic Relevance Detection. The model automatically determines the relative importance of each input dimension. This provides crucial scientific insights into feature sensitivity. It can tell you which parameters are driving the changes in your material's properties. It can even suggest where you might need to sample more densely for features with small length scales. This ability to adapt to the different sensitivities along each dimension helps GPARD models generalize much better than isotropic models, which are forced to apply a single, uniform smoothness assumption across all features.
That sounds incredibly powerful. It's not just optimizing to find the best result, but also helping you understand the underlying science of why it's the best result by revealing feature importance.
Exactly. It bridges the gap between pure optimization and gaining deeper scientific insight, which is invaluable in the discovery process.
We've painted a really exciting picture of how AI and ML are revolutionizing materials science and manufacturing. But it's certainly not all smooth sailing yet. What are some of the current hurdles and limitations that researchers and engineers are still grappling with when trying to implement these powerful tools effectively?
That's right. There are definitely significant challenges remaining. Despite the massive generation of data we talked about, One of the persistent hurdles is still data quality and quantity.
Still, even with all the data being generated.
Yes. Data specifically curated for ML applications can often suffer from noise, bias introduced during collection, or incompleteness, like missing metadata. And obtaining large amounts of high-quality labeled data, which is essential for supervised learning, remains a costly and time-consuming bottleneck in many experimental fields. You need reliable ground truth to train robust models.
I can imagine that trying to integrate these complex models into a real working factory environment or scaling them up for industrial use must present its own set of challenges.
Absolutely. Scalability is a major practical concern. Training complex models, especially deep neural networks, requires significant computational power. But beyond just training, deploying and maintaining these models at an industrial level requires extensive computational resources and a robust infrastructure capable of handling continuous data streams, real-time analysis, and decision-making. It's not just about building a model once, it's about integrating it reliably into live production systems.
And what about how well these models hold up over time? Factory conditions change, new materials come along. Can models trained on past data always cope?
That touches on the challenge of robustness and generalization. Models trained on historical process conditions may struggle when faced with new materials, new equipment, unexpected process drifts, or unforeseen events. Ensuring these models are adaptable and can perform reliably in dynamic, real-world manufacturing settings, maintaining their accuracy over time is crucial for their long-term effectiveness and trustworthiness.
And you mentioned earlier this black box problem. The difficulty in understanding why a model makes a certain prediction. Is that still a major limitation, especially in these critical manufacturing or design areas?
It definitely is. Interpretability, or the black box issue, remains a significant challenge for many of the most powerful ML models, particularly deep neural networks. Their internal workings can be incredibly complex, making it hard for humans to intuitively understand their decision-making process or explain why a specific prediction or recommendation was made.
Why is that lack of transparency such a problem?
It can seriously hinder confidence and acceptance, especially in safety-critical applications, think aerospace components, medical devices, or even critical semiconductor processes. If you can't understand or verify how the AI reached its conclusion, it's difficult to fully trust it, particularly when things go wrong. We need methods to open up these black boxes.
And who are the people bridging the gap? The ones who understand both the complex material science or manufacturing processes and intricate AI algorithms.
That points to another bottleneck: domain expertise. There's a crucial need for individuals who possess a deep fusion of both ML algorithm expertise and profound domain knowledge, whether it's in organic chemistry, semiconductor physics, or process engineering. Finding people with strong skills in both areas is currently quite rare. This really underscores the necessity for much greater interdisciplinary collaboration and perhaps new educational programs designed to train scientists and engineers with these dual skill sets.
A need for more bilingual experts, so to speak.
Yeah.
Are there any other limitations specific to the ML models themselves, or maybe the data they often encounter in these fields?
Yes, beyond those general challenges, specific model limitations exist. We've touched on generalization issues, models failing on data that's different from the training set. There's also the risk of underfitting, where the model is too simple, or overfitting, where it's too complex and learns the noise. These can often be exacerbated by data imbalance, which is common in manufacturing.
Data imbalance, like having lots of data on normal operation, but very little on rare failures.
Exactly. If you're trying to predict rare but critical events like catastrophic tool failures or the formation of a very specific defect, your training data might be overwhelmingly dominated by normal examples. This makes it very difficult for the model to learn the patterns associated with those rare events, potentially compromising its reliability when it matters most.
Okay, so a fair number of hurdles still to overcome. Knowing all these challenges, what's the path forward? What does the future vision look like for AI and material science in manufacturing? How do we tackle these issues?
There are several really promising directions. One that's gaining a lot of traction is physics-informed machine learning, or PML.
Physics-informed, how does that work?
PML aims to bridge the gap between purely data-driven ML and traditional physics-based modeling. It does this by explicitly integrating known physical laws, conservation principles like conservation of energy or mass, symmetries, or other domain knowledge directly into the structure or the training process of the ML model.
So embedding physics rules into the AI.
Essentially, yes. By doing this, PML can often overcome the low data availability problem because the physics provides strong constraints, guiding the model even when labeled data is scarce. It can also help solve complex, ill-posed problems where purely data-driven approaches might fail. In some cases, PML models can even outperform traditional physics-based simulations alone. Physics-assisted transfer learning is one example, where physical knowledge helps a model adapt to new, related tasks more quickly.
That sounds like a really powerful way to make AI more robust and data efficient in scientific domains. How do we build more trust in these models, especially the complex ones?
Developing robust techniques for quantifying uncertainty and ML predictions is absolutely vital. It's not enough for a model to just give an answer. We need to know how confident it is in that answer. Reliable uncertainty estimates allow researchers and engineers to assess the risk associated with a prediction and make more informed, risk-aware decisions.
Knowing the error bars, essentially.
Exactly. Another key area is multimodal data fusion. Future systems will increasingly need to combine diverse data types, maybe sensor data from a reactor, imaging data from a microscope, textual data from process logs, and numerical data from simulations to get a more comprehensive understanding of the material or process. Fusing these different perspectives provides a richer context for the AI models.
And making those complex multimodal models more transparent.
Yes, the push for enhanced interpretability must continue. Techniques like attention mechanisms, which highlight which parts of the input data the model focused on, feature importance analysis, like we saw with GPIRD, and advanced visualization tools are all crucial for making these sophisticated models more explainable and trustworthy.
Looking beyond just optimization and prediction, what other broader impacts might AI have in these fields in the future?
The prospects are vast. AI will continue to accelerate the discovery and characterization of entirely novel materials with unprecedented properties. We'll see the creation of highly sophisticated digital twins, virtual replicas of physical assets like semiconductor processes or even entire factories.
Digital twins, what can you do with those?
These digital twins allow for virtual testing, validation, and optimization of processes before implementing changes in the real world, dramatically reducing experimental costs and development time. We'll also see more sophisticated real-time process control systems that continuously monitor production lines and automatically adjust parameters for optimal performance and quality.
Smarter factories.
Definitely. And potentially even collaborative learning systems. Imagine using techniques like mixture of experts or advanced graph neural networks to allow different production lines, maybe even in different factories across the globe, to share insights and learn from each other's experiences without necessarily sharing sensitive raw data. This could optimize entire global manufacturing networks.
So it's really about making the whole ecosystem smarter, more efficient, and maybe even more environmentally friendly.
Precisely. By enabling these unparalleled levels of optimization and predictive control, AI can also play a significant role in optimizing resource usage, minimizing waste streams, and improving energy efficiency, contributing to a much more sustainable material science and semiconductor manufacturing industry in the long run. Hashtag tag tag outro.
So what we've really explored today is nothing short of, well, a revolution in progress. Artificial intelligence and machine learning are fundamentally reshaping materials science and semiconductor manufacturing truly from the ground up.
Yeah, from virtually designing individual molecules with exquisitely precise properties, all the way to optimizing the most complex multi-billion-dollar factory processes, the impact is already undeniable, and it's clearly accelerating.
It's clear that AI offers this unprecedented power to speed up discovery, to refine production in ways we couldn't before. The ability to predict how a material will behave, to screen millions of potential candidates almost instantly, and even to proactively prevent manufacturing failures before they happen. It's truly changing the game for how we invent and create new technologies.
It really is. But, as we've emphasized throughout this deep dive, this isn't just a story about machines taking over. The human element remains absolutely critical.
Right, that collaboration between deep human expertise, the intuition, the scientific understanding, the contextual knowledge, and the sheer computational power and pattern-finding ability of machine intelligence. That partnership seems paramount.
It's that synergy that's really pushing the boundaries of what's possible, unlocking new frontiers and innovation far faster than either could alone.
And that leads us to a really fascinating final thought for you, our listener, to mull over. As AI continues to learn, to evolve, and as our collaboration with these increasingly intelligent systems deepens, what truly new materials breakthroughs might it unlock that perhaps we can't even imagine today? And how will those fundamental advances born from this human-machine partnership further shape every facet of our daily lives?